Welcome to part 15 of the tutorial series. In this episode we are going to deal with Raster Music Tracker modules, which are the de facto standard format of having music, multi-channel music on the Atari 8-bit. So the Raster Music Tracker is a tracking program, a tracker, that allows you to create 4 or 8 track music for the Atari on your Windows machine. So it is a Windows executable that you can download from the website of Raster, who unfortunately died in 2011 at a very young age. And therefore the version is of the tracker itself, it's version 1.28, which is the de facto standard version that you should use. There is a project on Atari Age ongoing to continue the development of the tracker, but that's out of scope of this tutorial. So here you can download a zip file, and that zip file will contain the Windows executable. It will contain sample sources for the players, documentation, demo songs, and instruments. So I have it already installed on my machine. If you are a musician, you would use the tracker directly. If you are just using a Raster tracker module, you will still need the tracker for reasons I will show you in a second. Because it is the de facto standard, we are in a very fortunate situation, and I do something that I didn't do in any of the previous episodes, and that is we are looking at the examples that are already provided with the mat assembler. They are part of the Woodson installation. So there is the assembler, mats, there have your examples folders, which has a players subfolder for the replay code of the different standard players that were available for the Atari. Most of them were Atari native trackers, so people used the Atari to create music on the Atari. As opposed to that, Raster Music Tracker, as I mentioned it, is a Windows program that you run on a Windows machine, and it generates a sound file that you can then use in the Atari code. Technically, Raster Music Tracker files have the file extension RMT by default, and there is a description of the format, and effectively they are binary files consisting of multiple segments. As a consequence, when you store or save a Raster Music Tracker module, you give it a start address, and the data in the module is linked to that address, and that you cannot by default use it at a different address. The nice thing about the examples provided with mats is that it in fact also includes a macro that allows you to relocate an RMT module to an arbitrary location in your memory, so you can put it where you actually have some space left and don't need to stick to what the composer did. There is also a replay routine, which is rather big, as you can see here included. That replay routine is special in that it contains a lot of conditional assembly to optimize the resulting player to one specific module. That's different from other players where the same player is used for all modules of that type. Here the player is customized to particularly save space and do some tweaks at runtime depending on the individual module that you're playing. And also part of the mat assembler examples is a complete demo program that comes with an RMT file and with a so-called feature export. And I will do the following now. I will copy all of these files that we will need from the demo location to the tutorial. So that includes the RMT file and the corresponding feature file. Then we have the demo program and the demo program itself, it refers to the player, to the feature, to the module, and to the RMT locator, which is included down here. So we need this RMT relocator, and we need the player also in our working folder. So let's refresh. And the first thing that I do is I rename these things a little, because I prefer to have standard file name extensions. So all of these are Rmt's assembly source code, so I name them accordingly. So what do we have here? We have the Relocator, which is a single file that contains a macro. This macro takes the name of an RMT file and the new address where it should be located. And here you see there is some magic that provides compile time translation of the RMT file to the desired location in RAM. Then we have the Rmt Player itself. The player itself is completely self-contained, except that it needs the RMT feature file, which here is called music.fet, and it needs one input from you from the outside, and that is how it should deal with the number of tracks. Typically the tracks that you will have will be 4-track single pokey modules, which means they are mono, and then there are things variants where there can be 8 tracks. It's called stereo, and you need 2 pokies in your Atari machine for that. And for these 8 tracks, and for 4 tracks, there are 2 variants how they can be distributed between left and right channels. They are typically uninteresting, so in our example we will just work with the mono file, and that's it. What's important to know is that the Raster Music Tracker standard player uses the org statement to define its variables. So here the 0-page locations are starting here at 203 and counting up. I think there are about 20 0-page locations needed. Then we have here the player, which is the address that you would normally want to specify also from the outside, like the stereo mode. So what else do we have? We have the player, we have the relocator to relocate the RMT file. So now let's look at the RMT file with the hex editor. What is it? And as I said, the RMT file is essentially, from its structure, a normal Atari segmented executable file, except that it does not only contain executable code, but it contains the actual raster module. An raster module, as in the file description, always starts with RMT and then 4 or 8 depending on the number of tracks, and then there is the actual music information. I have installed the I can open the raster music file directly from Woodson IDE. There is a built-in sound editor that can replay RMT files. And here you see that it detects a format, which is RMT. So let's pause this for a second. There can be additional information in an RMT file about the title and the author. This is currently not in here. We see that it's mono, which means 4 channels. There is a music address where this was originally saved for, which is 4000. And we see that the replay frequency is normal 50 Hz PAL. Here we see that there is one song in this module. There can be multiple songs in a single module. One of them is the default. It has a duration that is computed here, and it can have a loop flag, which is here the case. And from here we can play, pause, and scroll to whatever location in the tune we want, and we have this ready. So then we have this feature file. So what is this? This is an export created from the Raster music tracker. So from the Raster music tracker, when you save the file for replay, you actually get two files. You get the module file itself as a binary file, and you get a feature file that contains now metadata about the module that is used by the player routine to decide which code is needed. If you don't use vibrato, like here, then for example the corresponding code in the Rmt Player will not even be assembled, and it will save you space, which can be crucial if you target 64K machines. So then how does the actual replay coding look like? This is the demo for the replay, and if we go down here, we see, well, there is lot, there is a table, and there is vcount, and there is a lot of things. Actually, you don't need 90% of this in most cases, which is why I'm not going to use this directly. Instead, I will cherry pick the relevant parts and put them into the part 15 demo. So why does this complexity exist? Well, Raster Music Tracker is very powerful. In particular, it allows not only replaying at standard speed, which would be 50 Hz or 60 Hz on PAL or NTSC machines, but it allows for multi-speed replay. So if you're a talented musician and you need very expressive instruments, you need to update things like the frequency and the volume of the envelope more frequently than 50 times a second, and therefore you can have it at 100 or 150 or 200 Hertz, and that's what exactly this table here stands for. It's the number of scan lines before the next iteration of a play routine call takes place. But for almost everything that I know or have used in my life, 50 Hertz replay is just fine. Particularly if you want to use it in a game or something, then we will have in a later session episode see how to include this in the interrupt, because you don't want the speed of the music to depend on the actual gameplay. You want it to be at constant speed, and therefore the vertical blank interrupt later will be very suitable. So what do we need? So let's start cherry picking what we need in our actual code. We will need the definition that we are replaying a mono module on a mono machine. That's the first thing. Then we need the macro to relocate the corresponding module to the right address. Then next we need the feature file and the module itself. So after we have the routine to relocate, we have the feature. We can put the feature file first. So this is just definitions. This would be the real module, and this is the relocator, and then we need the player. The player is in the player include. So this together is now all the information needed. Let's adapt the file names to what I did. I prefer lowercase labels. We put this here. We need an origin, and typically I always say we put the origin at 2000 because it's the lowest standard address that does not conflict with DOS. RMT has one caveat, and that is it uses the space before the player. So let's call this player, and we're in the same folder, so I don't need these. So here we have to comment out the player definition because we want to specify the player address from the outside. And here you see something where it says origin player minus 4000. And what that does mean is also described here. The player needs 1 kilobyte of working memory at runtime. And the way it is coded is that it assumes that the 1 kilobyte before the player are unused. That's why we have to increase the loading address by 1 kilobyte, so the space between 2000 and 2400 is usable by the player as a scratch pad. Yeah, then we have the module. Sounds okay. And what I always like to do is I like structure. So I call this music, and then we get here in the outline the corresponding context that's then called music. So let's see if this compiles. It does. What is the output? Yeah, here we see that there is some data in the range of 2000 to 2300 FF. That data is table data of Raster Music Tracker itself, and then at 2400 it starts with 4C, 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 4C. What this is, it's a jump table. So to have, like in an operating system or on the Amiga OS or also even in the Atari operating system, to not have to adapt the calling code when you change the player routines themselves start with a jump table. And the relevant things that we need to do are all after a table, after a label that is called Raster Music Tracker. So here we see there is a jump table, and the most important routines, the only two that we will use today are the init routine and the replay routine. There are additional routines to do things like replaying sound effects, setting everything to silence, or separate the update of the Poke chip from the actual replay. We don't need that. We just need this tell the tracker where the music is and then play it every 50th of a second. So we have Raster Music Tracker, and here we now use these scoping features of Mats that I really like to use. The actual Raster Music Player code is in XASM format for compatibility reasons. That was never changed. That's why I prefer to wrap it here. So we have here an init song routine that starts at Raster Music Tracker +0, and we have a play. Oh, let's call it init music. Init song, or just call it play. And that's at Raster Music Tracker +3. So what we need to do is we need to now really call these things. So again, we need a main program that we can start. And in that main program, we need to initialize now the player to tell the player which module and which song to play, because you could have multiple Raster Music Tracker modules, or one module could contain multiple songs. So you have to tell the system what you want. So we want the address of the music, which is module, and that is parsed as a combination of X and Y register values, so the low byte and the high byte. Then the first song is song 0, and we call music init song. Then it will be quiet because nothing is still played. We need to play it in a loop. And in that loop we need to call the play routine. And like in the previous example where we had the sound effects, we need to delay, of course, for 1 frame because it's a 50 Hertz tune, so we need to wait a 50th of a second. So let's copy that wait routine. Didn't copy the definition or T-clock. Looks okay. Let's check the executable. So the executable has become a little longer because now our main routine is there and the start segment is there. So let's close it all and hope for the best. I haven't opened the file, so it doesn't know what to compile. And there we are. And right from the start it works. Here you see the different channels, 1, 2, 3, 4 of the mono module and what they're currently replaying, and you see these complex waveforms that of course you cannot create if you do it manually like we did in the previous section. Yeah, this is a very short module, it's just 15 seconds, then it's looping. That's the effect you see. And the last thing that I would like to show, because it might be relevant for using this in an actual game or even demo. Currently we are waiting until the vertical blank, and then we don't see how long the replay takes. So instead of waiting for the vertical blank, I do now the following. I'm not waiting for the vertical blank, I'm waiting for a certain line on the screen. So this is somewhere the upper part of the screen. This should still work. I don't know. I should wait until we are there with a branch equal. So we're waiting for a certain scan line and then we start the replay. B and A. There we are. And what we can do now is we can say we want to see how much time it takes to actually do all the computation of the next set of Poke registers. To that end, we are now moving a red to the background color, and then we're resetting it again. So D0, 1A is the background color. And here we see this red bar. That's the amount of time counted in scan lines that it takes to replay. Yeah, and you see the more complex the tune gets, the longer this period can be. And that's one thing why I want you to mention it, because even if you do it in the vertical blank, so you have a constant replay like you will do in the next session, you have to be careful that you don't overrun the begin of the screen, because it might cause flickering or DLIs conflicting with your vertical blank. Yeah, but that's it. It's simple. It has some things you have to know about, like the 0-page addresses that are used implicitly, like the specification of the player address, the relocation, and very careful, these 1K of data that you need in front of the player routine. But other than that, that's it. So have fun with your first Raster Music Tracker replay. Bye.